Welcome to this short video that will cover these two activities and some basic plotting practice and using curve fitting and plotting tools within the Part D lecture notebook of Module 02. So I'm going to go ahead and just run all cells because that's going to involve some importing commands that I need. And so with the plotting practice, what you'll see is that I ask you to, or I suggest that you refer to the PyPlot tutorial here. If you click on this, it's been moved. Okay, so here's the link here. There's just useful plotting commands and examples and little nice tutorial that you can read through here. And especially helps with some of these things that I'm asking you to do. There's a lot more options available than just the things I'm asking you to do. The first thing I ask you to do, there's 4 pieces to this. The first one is to copy and paste the code cell plotting f of x equals x times sine of 1 over x, x raised to the negative 1 power below. Well, that would be this code cell here. So let's just go ahead and copy and paste it. So let me copy it. And here we go. And now I ask you to plot the function using a thicker red dashed dotted curve. So here's where the plot is. Notice there's no, let me fix some of these plotting commands. So there's actually the requisite 2 spaces. That's standard. So when I plot y, I'm plotting y versus x. Y is equal to this, x times sine of 1 over x, x raised to the first power. If I want to make a thicker line, I can use LW or line width. Line width is what I like to do because I just like to be explicit. And let's say I make it 4 instead of whatever the standard line width is. If we just plot that, notice how much thicker that line is compared to this line, right? What does 1 look like? That looks pretty much like what the standard line width is 1. So you can imagine the default is 1. And if I go 1.5, you can do floats as well. So there's 1.5, here's 1.95, which is going to look fairly indistinguishable from a line width of 2. I just say make it thicker. I would say 2 is definitely thicker, but you really want to go real thick, 4. I mean, you could go nuts here. Like if I make 10, it just looks like you used a fat marker to draw it. But I think, 4 kind of gets the point across. That's a thicker line for sure. If you want the color to be red, I said make it a red dash dotted curve, thicker red dash dotted curve. So now it's thicker. Now I'll make it red. So I'll use C for color. There you go. I think maybe you can also say color. I think there's usually a lot of options. Yeah, color or C. So I could say C here, just like I could say line width. I could use LW. So you can use these little these little shorthand. I often use line width, but I often just do use C for color. It's kind of up to you what you want to do. And then the line style, I want it to be, in this case, a dash dotted. I think in that case, I want dashed dotted like that. There you go. It's a dash, a hyphen, and then a dot. If you try doing it the other way, I don't believe it will work. So if I go dot dash, notice there's a value error there because it doesn't know what the heck to do, and you get a big value error. Notice it says this is not a valid value for LS, I guess for line style. So you could also use LS here instead of line style, just like you could use LW here for line width. So maybe I'll go to use that shorthand, but I kind of like saying line width and I like saying line style. Notice it in this error command, it's actually quite useful. They tell you exactly what the supported values are. So you can do a dash, 2 dashes, a dash and a dot, or a colon, which will produce a dotted line. At the same time, you could just spell out solid, which is what the single dash will do. That will actually be a solid line. This will be a dashed line, dashed. The dash dotted will be a dash dot line. That's what I was showing before. And this will produce a dotted line. And you could just spell out again dotted. So you have these options. And so here, right, I could say dash dot, and there's your dash dotted line. So I often, in this case though, I do like to just have, there we go, dash dot. So there's my dash dotted line. So I've accomplished the first 2 parts. I also say add X and Y axis labels. So in that case, let me just go ahead and create some new lines. Say plot, let's say X label. And, you can say anything. This is the X axis. Notice I can use some tech in here, like $signs, just like we've seen in the first lecture. This is the x-axis. Notice it puts it right there. This is the x-axis. See how the x is a slightly bit of a script? You might want to make it so it's even larger. So let's make the font size maybe like 14. This is the x-axis. Notice it's kind of like italics. Look what happens when I get rid of the $sign. Look how it's just kind of a regular square font, but it's more of a math font, more italicized, like if I have the $sign there. And I mean, that's silly. You could just, just X values maybe is what to do. So the X values are there, values. And then the Y label, I'm just saying anything, so Y values. I'm just asking you can put anything you want, really. And I'll make that a 12, just so you can see it's a different size if I do that. So that's all the coding. Now, I do ask you to add and edit comments to at least 3 different lines of code to explain what they're doing. So you should probably add a comment. I would say edit this one. This is what you should really edit. You should edit this code comment right here because you've edited this code, and you should explain maybe what line width, C, line style, or LW, color, LS, however you're calling them. You should have some information in your code comment for yourself to say what's going on there. You should add a code comment here, like this, the string is what is printed, and the font size sets the size of this X label. And then maybe say something similar for this code comment. In general, for the code commenting and the markdown interpretations and such, I'm not going to present those in these videos. I'm just suggesting what you should do here as a point of reference. So then the next activity that we get to is down here where we're using some curve fitting and plotting tools. So again, I provide some documentation that you can link to. It's involving the polyfit function in NumPy. What's nice is in this documentation, they even have some examples that are very simple for you to look at about how things are created. And so I recommend you can go through these. You can take each of these things. If you copy and paste it, you're going to have to remove, I think, these caret symbols here. But you could take that and figure out how to, mess with some plotting, but also how to basically create a polynomial that is evaluated and used for plotting. You can make your own code cells above, like you could say, why is this here? There we go. You could have like a little markdown here. You could say, this is my activity using polyfit. And then you could go ahead and put some of the material from here inside of some code cells to play around, make it interactive yourself, because this is not editable here, but you could copy and paste it and play around with it here. I highly encourage you to make these notebooks your own, add your own experiments. But at any rate, polyfit, it performs least squares fits of polynomials to data. So least squares is a type of regression that is very common in the computational and data sciences, and it is heavily used in machine learning, artificial intelligence, statistics, etc. In the code cells below, num_data denotes the number of data points used to fit a polynomial curve to the noisy data defined by x data, y data, where the x data belongs to the interval -4 to 4. You are to finish the code cells below such that a scatter plot of x data and y data is generated. A third order polynomial is fitted to the noisy data. You can read the polyfit documentation and look over the examples to see how to use poly1d to generate a polynomial function p from the output of the polyfit function. Again, this is where going through this is useful. You will notice that what they do is they create some data here. They do the polyfit, and the output is this z, and z is an array. It is a NumPy array. And if you look at these outputs, the point of the output, if you read this documentation, is the output P, the output array. That's what's returned. You could say it's P. They called it Z in that example. But these are the coefficients of the polynomial ranked from the highest order to the lowest order in the polynomial. And so then these are just numbers, coefficients for a polynomial. Feeding those coefficients into poly1d makes a polynomial function. Notice this is now a function. It has parentheses. You feed it inputs. These are like x values. And this creates an output, right? It's evaluating the polynomial whose coefficients are defined in this way, from highest order to lowest. So that's pretty much all you need to know in order to do this activity. I ask you to also use linspace within NumPy to create a regular uniform grid of 100 points in -4 to 4 called xgrid, and plot xgrid and then that polynomial function evaluated on xgrid on the same plot as the scatter of the noisy data. So let's just go ahead and start doing this. Notice I'm also asking you a question here that you might want to answer in the code comments about what is the difference between NumPy, the rand function within the random subpackage of NumPy, and the rand_n. The answer is that this is a random normally distributed number, and this creates a uniform random number, which are very different things. So here, all of this works so that you don't have to do anything in this code cell. So we can just run it. It's already been run because I ran all the cells before. Now, if I run this code cell, it will not work because there's missing pieces. Notice I say exactly what to complete. I'll just go ahead and fix these up. You are to complete this part, this part, this part, and this part, and this part, right? So there's empty things here in these various lines of code that you need to fix. So remember what I asked you to do. Create a scatter plot of x data and y data. Complete this plot to plot the y data versus the x data. So all you have to do here is say x data, y data. I usually don't have the space in the first part, but there you go. To x data and y data. So something like that will create the scatter plot. So if I just run it here, it will at least run through these two lines of code, and it will have an error starting here because I don't have any arguments that are correct here. So this should probably produce a type error is my guess. In fact, no, a syntax error. Okay, it doesn't like it. I guess it's empty. Then there's some definitely incorrect syntax there. I think if I got rid of those commas, it would produce no, it still is. Oh, I guess it just is an empty polynomial, so it would still work. Okay, so that creates the scatter. So I have the scatter plot. It hasn't actually plotted it yet. It basically exited when it reached this error. Here I need to create the polyfit to the x data, y data. So again, if you look at the example, right, it says fit x and y. So here's your input and output data. And here they're creating a third order polynomial, which is exactly what I asked you to do. So you just have to put x data here, put y data here, and then put a 3 there. Then you just have to feed that z array of coefficients into here to create the polynomial function p. And so that is so far doing these two parts. And now we just have to do this last part about using linspace to create our grid of values that are plotted. So I want to create from -4 to 4, 100 points. And then I want to plot x grid, and I want to plot the polynomial function p of x grid. That's it. I run it. There's your output. So you see this curve and everything looks good. So the best fit by the regression, the third order polynomial is in red. It's a pretty close approximation to truth. It's a little off, of course, because you have noisy data and a finite amount of it. If you increase the amount of data, so let's say I went to 1,000 here and I ran it again, notice that the red and the black are almost on top of each other now, but I had to use a lot more data to get more accuracy in my line. That's, of course, understood from like lines of best fit in standard regression. The fewer points you use, let's say if I use 10, the more error I'm going to have, the more deviation I expect to see between my curve of best fit, my regression approximation, and the truth, right? Notice how different the functions are now. Now also notice if I run this again, these 10 data points, if I run it again, I get completely different answers. And boy, does that look bad now. Now you might be seeing something different because I'm not setting the random seed anywhere. If you wanted this to be reproducible, you don't, again, 1, 2, 3, 4, 5, 6 is just what I always do for the random seed. You could put anything you want here. You could just put 1, 2, you could put, 7, 8, 9, whatever. You put any number you want. My default that I do, my habit is 1, 2, 3, 4, 5, 6. But if I put that in there and I run this, here's my approximation. Not too bad, but it's not great. And if I run this again, same thing, because I'm setting the random seed every time I generate this data. Of course, if I set this random seed in a different code cell and it wasn't here, so let's say I remove it and I put it here and I run this again, I'll get the same result because I ran that seed and then I ran this. But if I run this again, notice I get a different answer. You could rewind the video to see, but I think if you remember it all, it's definitely different this time. And if I run again, it's, boy, is that off. That looks terrible. So again, run it again. It's 10 data points. Here you go. It's off again and again and again. So that best fit curve in red is just kind of all over the place depending on what we're getting. So if I run this though, every time in a cell where I generate the data will always be the same unless I change the number of data points. But I think, again, 100 is a good number, and I'll just go ahead and I'll just get rid of that cell there. And you can just play around. Again, I encourage you to play around and experiment with it, but in the end, you might want to have your own code comments or markdown cells that are tracking the things that you're explaining. You might just want to leave this part standard fixed, like take that, and then all experiments you do, you might want to create new code cells here that you just copy and paste the contents from above as you change and play around with it. And I, again, highly encourage you, experiment, play around. That's how you're going to learn. Make it your own. Notice here, by the way, I have the color is black, line style, line width. Maybe you want to change this to LW, that to LS. Maybe you want to change C to color. There's all those different options. Notice how I'm setting labels to these plots, and those labels are necessary to create a legend. I can make the legend font size bigger or smaller. Maybe you want to add X or Y labels. I really encourage you to play around with these things because you're only going to get good at it if you do that. So that's it. Those are the only two required activities outside of the summary activity that you have to do, of course, on your own. So thanks for listening.